All right, hi everyone. Welcome back to the section 7.3 video. And in this video, continuing on the 7.3 series of videos, we are going to be discussing the inverse of the first translation theorem. So let's recall the first translation theorem that we learned in a previous video, and that is Laplace of an exponential multiple of f of t is just a Laplace of f of t, and s is shifting a units. So we want to use the inverse Laplace of this first translation theorem. So the inverse of this first translation theorem would be inverse Laplace of f of s minus a. What you want to do is break it down into just the f of s component and separate out the translation, the how many units you're shifting over. And so that would equal your original, your exponential multiple times your f of t. So f of t is just the inverse Laplace of f of s. So that's just the inverse translation theorem. So we're really just working backwards from the first translation theorem. Okay, so how to find the inverse is really this goal right here, these kind of recognitions. What we want to do first is recognize what the Laplace is, like f of s. We want to find the original function f of t by inverse Laplacing f of s, and then multiply f of t by that exponential function e to the at, where a is recognized by the units you are shifting s by. Okay, so it is once again hard to picture with the symbols at first. So doing an example would definitely clear up some confusion. So let's go ahead and try out example two, where we're going to inverse Laplace a Laplace function using the inverse translation theorem. So let's go ahead and try that out. So here we have the inverse Laplace of 2s plus 5 over s minus 3 squared. So kind of a spoiler, we're going to use partial fractions, and here we have a repeated linear factor. So s minus 3 right here, since it's being squared, it is a repeated linear factor. Okay, so we're going to set up our partial fraction decomposition. So PFD, we'll set that up. And so we have 2s plus 5 over s minus 3 squared. And it's a repeated linear factor. So what we would have is a over s minus 3 over plus b over s minus 3 squared. And so we want to figure out what a and b are. So we're going to multiply both sides by the least common denominator. So we're going to multiply by s minus 3 squared to both sides. And that would cancel out the s minus 3 squared, s minus 3, and then the s minus 3 squared on the right side. So what we're left with essentially is 2s plus 5 equals a times s minus 3 plus b by itself. So the way to figure out a and b, you've done this a lot through this course and your calculus 2. You could either equate coefficients, get a system of equations and solve for a and b, or you can choose values for s. I prefer to choose values of s. So I'm going to let s equal 3. This will allow me to find b. Because if I plug in 3, this would be 2 times 3 plus 5 equals a times 3 minus 3 plus b. This would make A go to 0. So what I'm left with is B equals 11. 6 plus 5 is 11. Okay, so there's nothing that would really cancel out B. We already know what it is though. So what we can do is just let S be something really easy. Let's just make it be, let's just make it 4 because, you know, 4 minus 3 is just going to be 1. So that's really easy to work with. So this would be 2 times 4 plus 5 equals A times 4 minus 3 plus B. Okay, so this would be 13 on the left side, just A plus B, but we already know B is 11. So that means A is just 2. Okay, so the inverse Laplace of 2s plus 5 over s minus 3 squared turns into the inverse Laplace of 2 over s minus 3 plus 11 over s minus 3 squared. Okay, so this is our new inverse Laplace. So what could we do now? What we could do to find these individually is separate them. So I'm going to separate them. I'm also going to take out their coefficients. So let's take those out. We would have 2 times the inverse Laplace of 1 over s minus 3 plus 11 times the inverse Laplace of 1 over s minus 3 squared. And so we want to figure out what these inverse Laplaces are. So 1 over s minus 3, well, that's pretty easy. We've seen that a lot. Okay, so let's go to our table to the right-hand side. 1 over s minus a, that fits this criteria here. So if I have 1 over s minus 3, what does that make my inverse Laplace? Well, that just makes it e to the 3t. Okay, so let's go back here. Let's write that out. And so this is just going to be 2 times e to the 3t. But our right side term, 1 over s minus 3 squared, that is where we're going to use that inverse first translation theorem. Okay, so how do we take care of that within the problem? So let's go ahead and see how that would work. So I'll call this psi. Okay, so 1 over s minus 3 squared. Well, if we think about that and we think about it in terms of shifting s left or right, what that is a Laplace of 1 over s squared shifted 3 units to the right. Okay, and since the inverse Laplace of something like 1 over s squared, well, what would that be? We actually have that on the table right here. 1 over s squared. Well, the inverse Laplace of 1 over s squared is just going to be t. Can it fits into this t to the n category? Okay, so we know it's going to be t. So let's go back there. Let's write that down. So since the inverse Laplace of 1 over s squared is t, then the inverse Laplace of 1 over s minus 3 squared, going back to our given question, well, what that's going to be is 1 over s squared, and we need to be careful with the notation that we are shifting 3 units to the right. Okay, so where am I getting this from? Well, this is the inverse first translation theorem. So I'll just write it right here. Recall the inverse f of s. S is shifting a units. Okay. Well, what does that equal? E to the at f of t. So what would this equal? This would just be t e to the 3t. Okay, that 3 is a, and 1 over s squared is that f of s. So therefore, the inverse Laplace of 2s plus 5 over s minus 3 squared is going to be what we found quickly, 2e to the 3t, plus what we just found now, te to the 3t. Oh, sorry, don't forget that 11. That comes down here as well. So 11t. So that is the answer. Okay, so that's our first exposure to the inverse first translation theorem, where we're using the first translation theorem backwards. So remember, just keep in mind your checklist when you're inverse Laplacing using this translation theorem, that we need to recognize what the Laplace is, find the function using inverse Laplace, and then multiply the function by our exponential multiple. So that's our first example of first translation theorem. Thank you for watching, and I'll see you in the next one. Take care.